Hello friends. In this video, we are going to study about the processor control instructions in 8087 coprocessor. These instructions are controlling the processes of the coprocessor 8087. So let's study these instructions in detail. The 8087 is the first math coprocessor developed by Intel to pair with the 8086 and 8088 microprocessor families. So this coprocessor, what it does, it provides very high speed calculations, and those calculations which are involving the complex numbers, because such types of calculations cannot be done by the microprocessors. So what the microprocessor do, they give these calculations to the coprocessor so that the main microprocessor is free from this task and its CPU storage and its efficiency is increased, because all these complex arithmetic calculations, they are now being performed by the coprocessor. Okay, so 8087, despite being of its a coprocessor, it is just like the main processor. Okay, like the microprocessor also has its architecture, its instructions, and its memory and address buses are there, and input output devices are there. So coprocessor, it also has its own architecture and it also has its own instruction set, and it uses the buses and the memory and CPU of the main microprocessor. Okay, so the 8087, it also has its own instruction set, and this instruction set of 8087 is classified into different categories depending upon the function performed by the instructions. So let's see that how the instruction set is divided into different classes. So there are 6 classes, okay, in which these instructions are classified. First is the data transfer instructions. These instructions transfers the data from one memory location to another location. Arithmetic instructions, they perform the arithmetic operations like addition, subtraction, multiplication, division, and the square root and absolute value is calculated. Then compare instructions, they compare two values, that whether the values are equal to each other or one value is greater or less than from another. Transcendental instructions, these instructions perform the trigonometric and exponential operations. Those trigonometric and exponential identities are calculated. Load constant instructions, they load the stack by a constant value. Okay, means the processor is loaded with a constant value. The processor control instructions, they involve the instructions which control the processes or the operations of the 8087. Okay, so this is how the complete instruction set of 8087 is classified into different classes. All the instructions, they are put into these different categories. Now the instructions of 8087, each instruction is having its mnemonic. Okay, mnemonic means that, like for addition, okay, the mnemonic is ADD. For subtraction, the mnemonic is SUB. Okay, so each mnemonic is prefixed with an alphabet F. So in 8087, if we are having the Mnemonic for the addition as FADD, for subtraction as FSUB. So every instruction mnemonic is starting with the alphabet F. Now this F it stands for the floating point numbers, because 8087 is dealing with the floating point numbers. So every instruction is starting with the alphabet F. Okay. So this was a general idea about the instruction set of the 8087. We saw that the instructions are classified into these 6 classes. So in this video we will study the last, that is the processor control instructions in the 8087. We will study that which of the instructions come under this category and what operation or function is performed by those instructions. So let us start with the processor control instructions. The first instruction is FINIT or FNINT. Okay. F is again the prefix for every instruction. Okay, every instruction will have F for the floating point numbers. Then INIT, this is for initialization. Okay. So what this instruction does, it initializes the 8087 coprocessor. So this instruction, first of all, it is going to initialize the 8087 coprocessor. At the time of initialization, the interrupt outputs, they are disabled. Okay, means all the interrupt outputs, they are going to be disabled. No interrupt will be active at that time. Okay, then the stack pointer, it is set to register number 7. In the 8087, we are having the stack which is group of memory location. The stack is consisting of 8 registers from 0 to 7. Okay, and each register is labeled like 000, 001, 010 till 111 for the 7th register. So at the time of initialization, the stack pointer, which is pointing towards the starting or beginning of the stack, that is at register number 7. So stack pointer, that is SP, is at register number 7, that is at 111. Stack pointer is initialized to this value, and then this instruction also sets the default status. In 8087, we are having the status register, which is a 16-bit register. The contents of the 16-bit register or status register is called the status word. And this status word defines the status, the current status of the 8087. So when this instruction is written FINIT, then 8087 is initialized, and when initialization is done, then the status is set as the default status, means all the bits, they will come to their default values. Okay, so this instruction, first of all, it initializes the 8087. When initialization is done, means interrupt outputs, they are disabled. Stack pointer is initialized to register 7 and the default status is set. Okay. Next instruction is FDISI or FNDISI. Okay, so this instruction, D is for disabling, I is for the interrupt. So what this instruction does, it disables the interrupt outputs. So this instruction is going to disable the interrupt output pin of 8087. When this pin is disabled, then no interrupt, that is no exception or error which is occurring in the 8087 can cause an interrupt to the 8086. It disables the 8087 interrupt output pin so that it cannot cause an interrupt when an exception error is occurring. In 8087, the errors which are occurring in the calculations, those errors are called as exception. Okay, now whenever any error is occurring in 8087, that error is going to cause an interrupt, and this interrupt is going to affect the main processor, that is 8086. Okay, so how it is going to interrupt, there will be an output pin called INT of 8087. This pin is going to become high, and then this pin is connected with 8086, so it is going to interrupt the main processor, the main microprocessor 8086. So when this instruction FDISI is written or FNDISI is written, then the interrupt output pin is disabled, means this INT pin is disabled. So when this pin is disabled, no error can cause an interrupt to the 8086. Okay, so it cannot cause an interrupt when an exception occurs. The pin is disabled. Okay, so this is the second instruction, FDISI. Then we are having the third instruction, FENI or FNENI. Now, just like the earlier instruction was disabling the interrupt pin, this instruction is going to enable the interrupt pin. EN is for enabling. So this instruction enables 8087 interrupt output pin. So that it can cause an interrupt when an exception occurs. So when this instruction is written, if any exception is occurring in 8087, that exception is going to cause an interrupt to the 8086, because that interrupt enable pin, that INT pin is now enabled. Okay, so this is FENI. Next instruction is FLDCW source. Now this instruction, LD is for loading, or we can say store. Okay, and then CW is for the control word. So this instruction is going to load the control word at the source location. Okay, so the next instruction is FLDCW source. So in this instruction, LD is for the loading, Okay, so this instruction is going to load the status word into the status register. So here we are having CW, that is control word. So this instruction is going to load a so control word is loaded from a memory location into the 8087 control register. Now this instruction is preceded by the instruction FCLEX. Okay, so that to prevent any of the exception, so this instruction, the FLDCW, it is preceded by the instruction FCLEX so as to prevent any exception response if any exception bit is set in the status word. Okay, so this is FLDCW, that is load the control word. Then we are having FSTCW or FNSTCW. Okay, this instruction is going to copy the 8087 control word to a memory location. First, the status word is loaded in the earlier instruction. Here in this instruction, control word is stored at some memory location. So ST is for the store and CW is for the control word. So it is going to copy the control word to a memory location. So the next instruction is FCLEX or FNCLEX. Okay. Now, as I have said that this instruction is written as preceded to the FLDCW instruction. Okay, and this instruction, it clears all the exception flags. So what this instruction is doing, it clears all the 8087 exception flag bits so that any exception response cannot affect the loading or the control word. So it is clearing the 8087 exception flags because these exception flags, they are causing the interrupts. Okay, so when we are clearing these exception flags means we are making the busy and the int outputs unasserts, means they are kept as low. Okay, now next instruction is FSAVE or FNSAVE destination. F is again for the floating point and SAV, that is save, is there. So what this instruction does, it copy the 8087 control word, status word, all those contents all these contents are saved or copied to 94 byte area of memory. Okay, because SAV is just for saving, that is copy the 8087 control word, status word, all its pointer, its entire stack registers, the that is copied to the 94 byte area of its memory. Okay, and after the storage, means after copying all this data, the 8087 is initialized. So we are storing or saving the current condition of the processor onto some memory location. Okay, all this data of the 8087 is stored in the memory, and after that it is initialized. Okay. Next instruction is FRSTOR source. Now here this instruction is going to restore all the data. Earlier all the data is saved to the 94 byte area of the memory. Now if we want to retrieve that data, then we will use the instruction FRSTOR, that is restore. Control word is copied to the control register. Status word is copied to the status register. Pointers are being copied to the pointer registers like instruction pointer, data pointer, stack pointer. Okay, and the stack registers, again they are copied into the stack registers. Okay, so all the contents which were earlier saved, they were again restored by using this instruction. Okay. Next instruction is FSTENV. Okay, this instruction, it again copies the eight zero eight seven control register, status register, its tag words, and its exception pointers. But now they are not copied to the 94 byte of area of the memory. They are copied to a series of memory location. So after this instruction, we are having the destination where all this data is being copied. Now you can see that in the earlier save instruction, the stack pointer, the stack registers, they are also copied. But here in this, the stack registers are not copied. Instead of them, the tag words and the exception pointers, they are copied. Okay. So this is a difference between the two instructions. In this instruction, no stack registers, they are copied. But in save instruction, stack registers are also copied. Next instruction is FLDENV source. Now earlier the data is copied. Now if you want to retrieve it, we can use the instruction FLDENV source. Okay, so all that data which is present at the memory location, that will be stored at the source location. That is from source, all that data will be again copied into the control register, status register, tag words, and the exception flags. So here at the destination data is stored, and here the data from the source is loaded into 8087. Now the next instruction is FINCSTP. INC is for the increment and STP is for the stack pointer. So this instruction is going to increment the stack pointer. Stack pointer is always pointing towards the top of the stack. Okay, so as I said that the stack of 8087 is having 8 registers. Okay, and these 8 registers are labeled from 0 to 7, and the top of the stack, that is ST, is pointed out by the stack pointer. Now suppose that the stack pointer, that is top of stack, is at register number 5. Now when this instruction is written, the stack pointer is incremented by 1. That means now the ST is the 6th register. Okay, again it is incremented, so stack top of the stack is now 7th register and stack pointer is pointing at that. Okay, so stack pointer which is pointing towards the top of the stack from where the stack is beginning, that is incremented by 1 through this instruction. Next instruction is FDECSTP. DEC is for decrement and STP is again for the stack pointer. So this instruction decrements the stack pointer by 1. So suppose that it is at 5. When it is decremented, now the ST will be at 4. Again, if it is decremented, now the ST will be at 3. So that is the top of the stack, or we can say the stack pointer. Okay. Next instruction is FFREE destination. Now this instruction, it changes the tag for the specified destination register. And this tag is changed to empty. Okay. So in 8087, as I have said, stack, there are 8 registers. Okay, so for each of these 8 register, there is a tag value which is specified as the tag word in the tag register. This tag register is of 16-bit. So for each of these 8 registers, there will be 2 bits, 2 bit for each register. Now these 2 bits, their tag values can be 00, 01, 10 and 11. These tag values specify that whether the register is empty, it is full, or it is loaded with a not a number value, unsigned value. So depending upon these tag values, the status of this register is known. Now when this instruction is written FFREE destination, then the tag value for the specified destination register that is changed to empty. When this tag value is 1 1, then the register is empty. Okay, so here the registers whose values is specified here, suppose that 7th register is specified. So 7th register, its tag value is changed to 1 1. Okay, so this instruction is used to change the tag for the specified destination register to empty. Now the next instruction is FNOP. NOP is for no operation. So this instruction, it performs no operation. No operation is going to be performed by the processor 8087. And what actually this instruction does, it copies ST to ST. Means the content of the top of the stack is copied to the top of the stack. Only copy procedure is done. Okay, or so we can say that no operation is performed by the 8087 basically. Next instruction is FWAIT, that is F wait. So this instruction, it basically what it does, it it makes the microprocessor 8086 to wait until the 8087 is compatible to communicate with it. Now when the 8087, it communicates with its main processor 8086. So 8087 is having a pin called the busy pin, and 8086 is having a line called the test pin. Now when busy is shown by the 8087, it means that it is busy in some operation. Right now it cannot communicate with 8086. And when this busy line is low and test line is high, then 8086 and 87, they communicate with each other. So if wait, this instruction, it make the 8086 to wait until it receives a not busy signal, means that this busy line is low, that 8087 is not busy, from the 8087 to its test pin. So when 8087, it sends a low signal at the busy line to the test pin of 8086, it means that now they can communicate with each other. Okay, so this instruction, it makes the 8086 to wait until this busy line is low. Okay, so these are the processor control instructions present in the 8087 coprocessor. So let's summarize these instructions, the processor control instructions in 8087. We studied these instructions with they control the processing of the processor 8087, like the initialization or the control word, status word, whether it is empty or busy or not. Interrupts are also controlled by these instructions. So under this category, we studied first the initialization instruction, if I NIT, initialization. Then for the disabling of the interrupt pin, BISI. Then for enabling, FENI. Then for the loading of the control word, storing of the control word. Then clearing of the exception flags, saving the control words and the status word into the 94-byte area of the memory, then restoring all that data, . then again storing the data and loading the data. After that, incrementing the stack pointer, decrementing the stack pointer, then changing the tag f free, f nop, no operation, f wait for the wait state. So these are all the processor control instructions. You can see that they are controlling the operations of the 8087, which are related to its initialization, for enabling the interrupts, for receiving the control words and status words and restoring them, for incrementing, decrementing the stack pointer, and for the no operation at the wait state. So in this video, we studied about the processor control instructions present in the instruction set of 8087 math coprocessor. I hope that this topic is now clear to you. Thank you.